Hey everyone, we are going to talk about the physics behind a rotary engine. In specific, we're going to be talking about particle dynamics, fluids, solids, mechanical waves, and sound, and how it applies to the physics behind a rotary engine. So let's get talking about this. So basically, the history behind a rotary engine is that this guy named Felix Wankel in the 1950s developed this engine that allowed for a smoother ride, and instead of using pistons, it used this triangular gear, and you'll see it in a diagram right over here. And it actually spins about counterclockwise through, or it could be clockwise, but it basically allows for gas to be intaken into the engine and be able to be blown up, and it'll move this triangular piece and allow for a smoother ride. But the deal is that it was a little inefficient. However, Mazda used it in the RX-7 and RX-8, so it definitely is used in some vehicles to this day. To begin with, when it comes to a rotary engine and particle dynamics, the way that particles interact with the engine is actually through the combustion process that is within the engine. So first off, there's an intake which actually takes the gas, it goes into the engine, it's compressed, so the particles are compressed, and there's a spark plug that actually ignites this gas. And with that as well, it's able to push that rotary piece, around a gear, and it continues that movement. And with this gas is able to be pushed right back out into the outtake, and it's able to continue that process, which in a basis allows for the engine to move really quickly. How it goes about doing this is using the ideal gas law, which you're actually able to calculate the pressure, volume, number of moles, and you're using the universal gas constant. And not only that, but you're able to calculate temperature, which actually is really, really cool, especially for this.
One aspect of the rotary engine that is really important is the coolant system. In the rotary engine, we see that there are these little things called water jackets on the very outside. In these water jackets, water is pumped through in order to cool down the whole engine. So in this, we see that it is caused, the water moving through the system is caused by something called a centrifugal pump, which is basically just a device that it kind of looks like a fan, and it's able to move the water forward, and then the water molecules that are behind push the water molecules that are in front forward, sort of like how if you push on a cart, the cart will move forward and the person behind is able to move it just like the pump would be like behind it, and then the little water molecules, and then the person moving forward. And this is super important. Fluids are critical in order to keep this engine stable, at a stable temperature, able to keep it moving and to keep it running.
How do solids come into play? Well, we do know that they are one of the 4 fundamental states of matter, and they are characterized by a fixed volume and shape, and so they are unlike gases and liquids. We also know that they are atoms that are tightly packed together, so they have a strong intermolecular force. And lastly, because of this, we know that they are very rigid. And so that means that they resist deformation, but they can bend or vibrate under extreme stress. So how does this come into play with rotary engines? Well, we need something solid, such as metal alloys, because they can resist extreme heat, pressure, and mechanical stress. To look at a diagram to kind of explain this further. What we have here is a rotary engine. We're looking at the rotor, the housing, and we also have the chambers, apex seals, and eccentric shaft. So what the rotor is made out of is usually a strong type of steel, and then the housing, we've got probably a aluminum or a strong steel similar to the rotor. And then for the apex seals is what's going to seal off the combustion. So we want that also to be strong, and it's usually a metallic sort of composite. So it's important for these though to be really strong solids, because it needs to be something that is resistant to heat, or that can deal with extreme amounts of heat and pressure. So that's usually what these are made out of, because in here we've got a lot of explosions going on in these chambers here. So everything around it, including everything surrounded by it, needs to be something strong and solid. So looking at this aluminum problem, we can see that how it is important to study each material and see the rate at which they expand given different temperatures. And so we can see here that aluminum would be 1.2 millimeters once it's from 20 degrees Celsius, and how much does it expand when it's heated to 120? So this is good data because we can see that, aluminum has a moderate expansion rate compared to other types of material. And so this is why aluminum and steel is also used. But I think engineers also opt to use aluminum more than steel in some cases, is because it's lighter and it dissipates heat better. Now that you understand how solids allow this engine to function, let's talk about how sound is a result of this. So as you can see on the board, it's characterized by 3 key features. First one being frequency, which is a pitch, high or low. Amplitude, it represents the loudness. And then lastly, wave speed, which can, change through different mediums, such as through solids, it's quicker, but through gases, it's slower. So rotary engines actually have a distinct sound. It's usually a high whirring sound, which is different from piston engines, which have a deeper rumble. So why is this? Well, we have 3 reasons. Combustion pulses. This happens every 3 times per rotor revolution, which equals higher frequencies sounds. Secondly, we have triangular rotor motion. This creates a continuous, smoother continuous vibration. Lastly, exhaust design, which can amplify certain frequencies. So we've explored how solids provide the structure needed for a rotary engine to handle stress and heat, while sound waves give it a auditory, unique signature. We've even calculated thermal expansion and sound frequency through equations, which are key physics concepts in automotive engineering. So looking at our example problem 2, calculating a sound frequency, we see that if we're given a rotor engine's rotor spins at 8,000 RPMs, if it produces 3 combustion pulses per revolution, what is the dominant sound frequency in hertz? So with some simple calculations, we can convert RPM to RPS, which will equal 133.33 RPS, and if we multiply by 3, the pulses per revolution, will get 400 hertz. So this is a high frequency, which explains why rotary engines sound like a buzzing bee compared to a piston's engine, which is like a rumble.
Mechanical waves are a disturbance or oscillation that travels through matter from one object to another or particle to another, transferring energy. And for example, when an object is dropped into water, it creates a rippling effect, and what that does is it shows that the water particles are moving up and down with the ripple. And what that does is it transfers energy from the wave to other particles around it. And in order for there to be mechanical waves, there has to be a medium, and a medium is either liquid, gas, or solid, but without that medium, there cannot be a mechanical wave. And there are 2 types of mechanical waves, that being transverse waves and longitudinal waves. Transverse waves are when the medium moves perpendicular to the wave's direction, and longitudinal waves is when the particles of a medium moves parallel with the mechanical wave. So that there is an equation for this, which can be described as the wave speed equaling the frequency multiplied by the wavelength. So how this works within a rotary engine is that we see this in 2 main parts, which can be the combustion chamber and the eccentric shaft and rotor. So within the combustion chamber, there are 2 spark plugs usually within a rotary engine. If there's only one, it would be too slow. So since there's 2, when those plugs ignite, a mixture of the fuel and the air, the mixture of the air and fuel ignite, causing pressure to build up within and moves the rotor, which then forms pressure waves, which is a form of mechanical waves. And for the eccentric shaft and rotor, as the rotor moves within an oval-shaped housing, it oscillates, causing vibrational waves, which is also another form of mechanical waves. So yeah.